Hello, everyone. Um, Today we're starting to talk about the bottom-up approach. And as you remember, we classified bottom-up approach into two, basically liquid phase synthesis and gas phase synthesis. And we will start learning about gas phase synthesis. And I divided this class into three sections, parts 1, 2, and 3, just to make things easier for you to follow. And so let's start our class for today. Here, it's important for us to be able to classify the nanomaterials using some terminologies. For example, we like to use the dimensionality approach. So we like to classify materials in terms of their dimensionalities as zero-dimensional nanoparticles, one-dimensional nanotubes, or two-dimensional thin films, for example. So it depends, everything depends on what you want to make in your lab. So if you want to make, for example, zero-dimensional nanomaterials, and if you want to create some surface features on a zero-dimensional material, you can go ahead and use the techniques called PVD and CVD to create these nanomaterials. This is physical vapor deposition and chemical vapor deposition techniques. Or if you have a one-dimensional nanotube, and if you want to create a surface feature again, you can go ahead and use lithographic methods. Or if you want to create two-dimensional films, but you just want to create something like a discrete nano-object, you can go ahead and use a top-down approach, beating, for example, or bottom-up approaches, electrodeposition, CVD, PVD, and self-assembled films, for example. So this is a general summary of how we classify things using what approach and which methodology. Okay. So let's talk about these things a little bit more. Different approaches for nanomaterial synthesis. The first one is top-down and bottom-up approach, milling, attrition, repeated quenching, lithography, homogeneous nucleation from liquid or vapor, or by heterogeneous nucleation on substrates. These are different top-down, bottom-up approaches that we already talked about a little bit. Or you can take a dimensional approach and say, okay, I'm going to make a one-dimensional nanotube or a zero-dimensional quantum dot, or I'm just going to make a bulk synthesis in nano size. Or you can say, okay, I'm going to take a gas phase, liquid phase approach. And for example, a CVD or inert gas condensation methods are gas phase approaches, while micelles and sol gel and self-assembly are the liquid phase approaches. So it's really important for you to have a general understanding of what these things mean in general and where you might need them. If we go into a little bit more detailed explanation of the synthesis of nanostructured materials, well, nanocrystalline materials can be synthesized either by consolidating small clusters, which is the bottom-up approach, or breaking down the polycrystalline bulk material into crystalline units, which is the top-down approach. In the bottom-up approach, we have to arrange the nanostructure atom by atom, layer by layer. These seek to arrange smaller components into more complex assemblies. However, in the top-down approach, we start with the bulk material and break down the microstructure into a nanostructure, and these seek to create smaller devices by using larger ones to direct their assembly. Okay, and there are a number of techniques that have surfaced over the years for producing nanoscale particles as well as bulk non-structured materials, but most of them are limited to synthesis in small quantities. So one of the important things that you have to keep in mind during synthesis is your aim in how much of that material you need to obtain. If it's just in milligrams, you can go ahead and use, for example, a bottom-up approach easily, because once you make things in the lab, you create small amounts of things. But if you want to scale up your synthesis, and if you want to, like, at the end, make tons and tons of products, you have to find a way for scaling up your technology, which can limit you. I mean, you can spend your years in the lab just to be able to make some very fancy material in 0.1 milligrams, but it's maybe really hard for you to produce it in tons. So these are, every approach, every methodology has its own ups and downs, advantages and disadvantages, and that's what we're trying to teach you right now in this class. And you already have an idea about how do we make things small, nanofabrication methods. This is, you tell me, top down, and this is you making things bottom up in your lab. So this is what we want to create. You can either go this way or that way. And we're going to talk about most of these methodologies in this class. So bottom-up can be chemical synthesis, self-assembly, positional assembly. Okay, and chemical synthesis is good in cosmetics, fuel additives. Okay, self-assembly is used in displays, for example. Positional assembly is used in molecular devices. Or top-down approach, we talked about it, lithography or cutting, etching, grinding, all sorts of things. Quantum well lasers can be made by lithography or computer chips or MEMS. Or cutting, etching, grinding can be useful for high-quality optical mirrors, okay? So we want to be able to obtain these things in a range of 1 to 100 nanometer. Should we go this way or should we go down in this way? As you know, a nanometer is 1 billionth of a meter. Materials that are referred to as nanostructures have sizes between 1 to 100 nanometer. Okay, so you have to have an idea about what to call as a nanomaterial. Okay, even if your nanomaterial is not in the size of 100 nanometer, you can have some features in that range that makes it, that gives it the nano property, which Bilge Hoca will talk about this Friday with you, okay? So when things go into the nanoscale, they change their properties, like optical properties, magnetic properties, electronic properties change. And it can be for good or it can be for bad, but you as a nanotechnology engineer, let's say, you have to know how they're going to change, how they're going to affect your life, in what way, okay? Okay, so let's continue. Just as a wall may be built up by piling bricks one over the other, particles may be created by assembling together their building blocks, which may be atoms or molecules, and that's what we're trying to do in nanotechnology, okay? This can be done much more easily by trying to break down a large particle, or it can be synthesized by bringing together atoms or molecules which are initially apart from to form a larger cluster of atoms. What you want to remember is what's important is this last bullet here, which says, however, things are not that simple and these particles quickly grow to be too large. It is thus important to arrest or limit, okay, this is important, to arrest or limit the growth of these particles when they have grown to be to the desired size. And this is how we control the growth of these particles. So how do we make things small? We have to find a way to limit their growth or some other means to keep their sizes in nano regime, okay? So top-down approaches include milling, attrition, repeated quenching, lithography, blah, blah. However, nanoparticles produced by attrition have a relatively broad size distribution and varied particle shape and geometry, okay? So this cannot be a very important parameter for you. For example, if you're in the nanocomposites world, all you want is to create an additional feature into your composite material. And let's say your matrix, you have a polymer, but you want to create some thermal enhancements in your composite material. You don't care what sort of nanoparticle you're putting into your polymer. Maybe it can have a broad size distribution, then you can go ahead and follow the bottom-up approach, the top-down approach, sorry, because the top-down approach may create you a varied particle shape and geometry. In addition, they may contain a significant amount of impurities from the milling medium and defects resulted from milling. And like it says, it's used in nanocomposites. Bottom-up approaches are far more popular in the synthesis of nanoparticles, and many methods have been developed. For example, nanoparticles are synthesized by homogeneous nucleation, which we will very deeply talk about in our coming classes, from liquid or vapor, or by heterogeneous nucleation on substrates. If you have never heard of these terms before, please look them up and try to have an idea about what we're talking about here, okay? So what are we trying to do? We are trying to confine what's happening in our little nano world. Nanoparticles can be synthesized by confining chemical reactions, nucleation, and growth processes in a small space, such as micelles. For example, this is just an example, okay? And there are two approaches that you can take to confine what's happening in your reaction, okay? The first one is the thermodynamic approach, which you control the generation of supersaturation or the nucleation and the growth of your material, or you try to control it by kinetic approach, and the way to do that is by limiting the amount of precursor, and precursor is the food that you are putting into your system for it to grow, okay? Available for the growth. When you don't give it the necessary food, it's not going to grow. So that's what you do. You limit the amount of precursor available for the growth. Or you confine the process in a limited space, and that's called the micelle synthesis. And this is a liquid phase approach, okay? So you try to form the bubbles. Okay, you create this size bubble or that size bubble where your nanoparticle grows, and then this will give you the control of your nanoparticle size. So let's say this is 1 nanometer versus this is 5 nanometer nanoparticle, okay? This is a very important slide for you to remember. That's the general requirements for nanoparticle synthesis. Because for the fabrication of your nanoparticle, small size is not the only requirement, okay? For any practical application, the processing conditions need to be controlled in such a way that resulting nanoparticles have the following characteristics, okay? These are important. This is what we're trying to do as researchers, as technicians, as nanotechnology engineers, whatever you want to be. This is the type that this is the properties that you want to control in your nanoparticles. So the first one is you have to decide if you want to have an identical size of all particles, okay? And the approach that you take for your synthesis has a huge effect on the particle size distribution of your nanoparticles. So you have to decide if you want to have a wide particle size distribution or a narrow particle size distribution, okay? And if you want to have an identical shape or morphology, okay? If you have never heard of this term before, please, again, look it up. So your particles can be in triangles, in squares, in circles or whatever, and each shape and each size, okay, each shape, each size, each morphology changes the results that you obtain from your application area. If you are working in the catalysis area, for example, it will change your catalysis results. The triangles will give a different different result than a square, than a circle, and the sizes will also change everything. Okay, let's clear this place up. And the third one is the identical composition and crystal structure that are desired between different particles and within individual particles, such as core and surface composition must be the same. So let's say you have again something like this. This is your nanoparticle, okay? And let's say the surface structure is different than its core structure. Okay, let's say this is, I don't know, this is gold and this is silver. Okay, so whatever result you obtain, you think that it belongs to your nanoparticle, but is it because of the gold or the silver? Okay, so that's why it's called such as a core and surface composition must be the same. Okay, it can't vary, otherwise you won't be able to control what you're doing with your material in your application area. And also the chemical composition is important. Okay, let's say you have like X grams of nanoparticles and you get some certain milligrams of your nanoparticle and use it in a catalytic reaction. Will it give the same result if you were to get that powder from a different part of your sample? Okay, so it has to be identical. So that's another important requirement to think about. And the fourth one is individually dispersed or monodispersed. That is no agglomeration. Okay, if agglomeration does occur, nanoparticles should be readily redispersible. And this is also very, very important because you will see, or you already had seen, that once you go into the lab and start making nanoparticles, they really like to come together. They really like to form agglomerates, okay? And so when they are all together, it becomes like a big particle. It's not nanoparticle anymore. Okay, so you want these little nanoparticles to be dispersed. Okay, you like them to be redispersible. So there are ways to control the dispersion of what you're making in the lab, but it can create some headaches for you. Okay, so these are the 4 very important requirements that you need to consider as nanotechnology people. And you have to be familiar with the terms like nanocrystals, quantum dots, and so on. If you've never heard of them, which I hope you are aware of these terminologies and concepts, then please try to read a little bit more of these things from your book and from internet. And we're gonna continue with the discussions on principal synthesis methods, inert gas condensation, inert gas expansion. Okay, we're going to talk about these. Sonochemical, sol gel, molecular self-assembly. This is bottom up. Physical vapor deposition, CVD, rapid solidification is bottom up. Milligan mechanical bottom up, micromachining, and so on. Okay, so we're going to mostly talk about the ones that I put a check next to it in the second part of our presentation. And please be familiar with how to differentiate these different techniques as bottom-up, top-down approaches. Okay. With that, I'd like to finish the part 1 of our introductory bottom-up approach, and let's continue with the second part.